Hello and welcome back for the video for lesson 4.2. And we are going to introduce a new function called exponential functions. And exponential functions, we're going to learn about how to define them, like kind of what they look like on the graph, a basic one, and then also how to find their main properties and parameters. An exponential function is a function of the form c, where c cannot be zero, it's some constant, times a to the x. A is your multiplier because it's a to the x. So your repeat multiplication is an exponent. So that's what we're doing is we're repeating a. It's like this. You've got your starting value c, whatever that is, and you're multiplying a any number of times. You're multiplying a x times. That's why it's to the x exponent. Okay, so a just has to be greater than 0. It cannot equal 1. And like I said, c has to be not equal to 0. So it says, let's evaluate 3 to the pi to 4 decimal places using a calculator. So we're just going to go and look at example 1 and 2 in Desmos quickly. This lesson is really mainly looking at just the basic parts of this function. So just reminding you that 4 to the third is a repeat multiplication. And then 3 to the pi is 31.5443 when we round appropriately. And then what if we just looked at 3 to any exponent? It looks like this graph here. You can see that it looks like it has an asymptote at y equals 0, and it gets extremely large quickly. And you can also see we made a table. So I'm going to show you again how to make a table in Desmos so you can see. Once you type in an equation, if you go up to the gear right here where my mouse is and click on edit list, then you can say make a table, an input output table. So we could put pi if we wanted. Pi is a symbol at the bottom of your menu here in Desmos at the bottom, right here where my mouse is. See my mouse? And it would give you that same value. You can see example 2 on your paper says, what happens to the value of the function as x approaches positive infinity? It goes up to positive infinity. And as x approaches negative infinity, it gets really, really close to 0. So we're going to write that on our paper. So let's go back to our paper so we can jot that down. So y goes to a positive infinity as x goes to a positive infinity. And y gets really, really close to 0 as x goes to a negative infinity. So what happens if we looked at this function, 6 to the negative x? So 6 is a positive number like 3 was, but instead of going to a positive x, it's going to a negative x. So let's go ahead and look at that in Desmos and make some observations. I'm going to turn off this graph here, and I'm going to look at the y equals 6 to the negative x. So this one is a little bit different. It goes to y goes to 0 as x goes to a positive infinity, and as x goes to a negative infinity, y goes to positive infinity. So it looks different as compared to the last function. And don't mind this because this is really more like right here. My x-axis and my y-axis here. So in the box down below, you can see some properties of the two situations. So this is important to note that it's when a is greater than 1. So when our multiplier is greater than 1 and C is greater than 1, it's an increasing. Okay. And then when when our multiplier is a fraction, it's going to be a decreasing function here. Okay. And that also happened, as you can see, that it was a negative x here. So that changed, this table here is not looking at that at all. It's looking at 1 over, because this is a negative x, this is the same as saying 1 over 6 to the positive x. That's why it was giving this shape. It's similar to this. Okay, so let's see here. So we have make an input output table for this one. So this is like saying -1 times 3 to the x. So let's look at this situation. So up here we have a is greater than 1. So we're actually in C is less than 0. So this is our C. We don't have that situation up here, but we do have A is greater than 1. So we have actually 4 pictures that could happen. So this is if A is greater than 1 and C is less than 0. Let's see what this looks like in Desmos. This one up and this one here. Okay. So this one is as it goes to y goes to a positive infinity as x goes to a positive infinity. Y goes to a negative infinity, pardon me, a negative infinity. I'm going to show you on my paper. And then y gets really, really close to 0 as x goes to a negative infinity. Going back to my paper so you can see, I misspoke. Y goes to a negative infinity. So that's this one here. Right. So C is less than 0 and A is bigger than 1 on that one. We have another number that similar to, we have the irrational number pi that we've worked with a lot in mathematics, but we're going to work with another irrational number. And as this ratio 1 plus 1 over x goes to the x exponent, gets infinitely large, then it increases and gets really, really close and becomes an asymptote at this number 2.718, 2818, 284, and it's got an endless number. And we call that number E. It's the natural number E. And usually we just go to 3 decimal places, 2.718. So let's make a table of the function e to the negative x. And get those here. E to the negative. So here's e to the positive x, but we're going to look at e to the negative x. So just going from e to the positive x to e to the negative x, it just changes the direction of where that's coming from. So we saw that in to the negative x was similar. This one right here was in a similar look to that. As this one. And so y goes to 0 as x goes to positive infinity, and y goes to a positive infinity as x goes to a negative infinity. So it's decreasing from left to right. It's decreasing from left to right. So just getting the idea of what the picture should look like. There are two particular instances where we use exponential functions, and they're both in money. We're just going to talk about those now. And then on the next couple lessons, we're really going to dive into the exponential function. But compound interest is one, and continuously compounding. So interest is money that you either pay for borrowing money. So sometimes it's the bank paying you because they borrow your money when you leave it in a CD account or a long-term savings account. And then you pay money when you borrow money. So you might pay interest to a bank when you borrow money from them for a car loan or a house loan, or you might pay money to a bank for a credit card if you don't pay your balance off every month. Or you might borrow money from your parents to help pay for college, and so you might pay them interest. Okay, so when you're paying interest or earning interest on previous interest, that's called compound interest because it's compounding. It's like a snowball. It gets bigger and bigger and bigger and bigger because just like a snowball, you're attaching more snow to the outside of the ball. And as the ball gets bigger, you have more surface area that you're attaching the snow to. And that's how compound interest works as well. So compound interest, this formula, R stands for your interest rate, and that's always in decimal form. And then P is the amount you're investing or borrowing. N is the number of times it's compounding per year. And then T is how long you're going to leave it in the investment. So sometimes it compounds once a year, so N would be 1. N would be 12 if it's compounding monthly. It could be N equals 4 if it's compounding quarterly. N could be 365 if it's compounding daily. If it's compounding weekly, then N would be 52. And then sometimes it compounds continuously. So if it went from N as 365 for daily and it just kept compounding even more, like hourly and then every minute and every second, that's called compound continuously interest. And that formula is here. We use the P, which is the amount you're borrowing or lending, and then the natural number E that we talked about up here. It's used a lot in financial formulas. And then I'm going to just write it bigger for you. It's on your paper, but it's E. And then make sure that R times T is in the exponent. In Desmos, you'll want to put them in parentheses to make sure that they both stay in the exponent. So let's look at a couple of examples to get you thinking about this. So, example 6 says, suppose $3,000 is invested in a savings account. Find the quantities. Amount in the account after 3 years if the interest rate is 6.5% and you're compounding monthly. So P is equal to 3,000 and our interest rate is 6.5, but that actually goes in as 0.065. And we're going to let it sit there for 3 years, and compounding monthly means that we're using N equals 12. So this is going to be A of 3 because T is equal to 3. It's our A function at 3. So we've got P, which is 3,000 times, making sure you're referencing the formulas correctly. Here, so 1 plus the rate divided by the number of times you're compounding per year. And then you're going to raise that to that same number of times you're compounding times the number of years. So let's go to Desmos so you can check out what that's going to be. And that is right here, 3,000. We put the formula in, make sure that your n times t is in the exponent. And so after 3 years, we would have $3,644.01. Always make sure you round to 2 decimal places because pennies count. And if you wanted to figure out how much interest you earned, you could just take that 3,644.01 and subtract away the 3,000 that you started with, and you would see that you earned $644 in interest over those 3 years. Now, compounding continuously, part B, is the formula of A equals P times E to the RT. And I showed that here in this line, 3,000 times E to the RT, which is 0.065 times 3. And so if they're compounding continuously instead of monthly, you're going to have $3,645.93. And so going from compounding monthly to continuous, let's just see how much more money we'd have. So there's after continuous subtracting the compounding monthly. And it looks like you're only earning $1.92 more by compounding continuous. So it does increase what you're earning, but not by a whole lot. There's your compounding continuous versus compounding monthly. Put 7. It says if a Ford Focus was purchased for $22,000 and depreciates at a rate of 10% per year, find an exponential function which gives its value t years after purchase and sketch the graph of the function. Okay, this is a little different because we're not actually growing, we're decreasing, and it's decreasing by a rate of 10%. So in an exponential function, we have f of x times c times a to the x. And c is our y-intercept. It's our starting value. A is what we're going to call our growth or decay factor. Okay, so if you are, and then this right here is our relative increase or decrease. It's depreciating, so it's a relative decrease. Where it's going down by 0.10 per year, okay? So our growth or decay factor is going to be equal to 1 plus our relative growth or decay. And so if it's growth, let's just write this in 2 ways here. If it's growth, then A is going to be bigger than 1. If it's decay, then A is going to be less than 1, but still bigger than 0, okay? So in this case, our relative increase or decrease, which is a decrease for us, R is equal to negative 0.10. So that means A is equal to 1 plus a negative 0.10 or a positive 0.9. Because it's retaining 90% each year, 90% and 90%, it's going down. So it says, we're going to write our function, it's going to be, they want it in terms of t instead of x. So the function in terms of t is going to be equal to 22,000. That's our starting value, our y-intercept, and our multiplier is going to be 0.90 to the t. And let's see what this looks like here. Let's type that into Desmos and see what we come up with for a graph. So y equals 22,000 times 0.9 to the x. And I want to see it on the graph. We don't see it, and that's because our y-intercept is so large. So let's just go up and make a table. And then when you make a table, it allows you to change the scaling by zoom fit over here to the bottom left with a magnifying glass. And that's really nice. And I'm just going to zoom out a little bit so I can see the big picture. So there's our starting value, and it's just decaying. You can see each year it's just going down by 90%. It's only keeping 90% of 22,000. So if we take 0.9 times 22,000, we get 19,800. And then if we take 90% of that 19,800, we get 17,820. That's the next value. So you're losing 10% each year. And that's how we come up with our function. So there's the function we came up with. So catch me back for another video where we're really going to expand on this exponential function.